Um, so congratulations, we're almost done with the semester. Today is going to be the last sort of class in terms of materials, so that'll give you guys time to catch up on areas that you're perhaps not too up on. We have two more classes though, and so those classes will be largely review. So what I would say is that I would, if there's specific things that you guys would like me to cover, feel free to email me if you want me to prepare for a specific area. Otherwise, I'll just come in and have a few things, probably feel recitation-y, and I'll throw up some problems up there, and we can sort of go over them together. So if you guys have specific things you would like me to focus on, if there's a specific area, again, if I get bombarded with emails and I can't meet everybody's needs, I'll just sort of look and see what, sort of by vote, what people seem to want to talk about the most. Yeah. Yeah, I haven't double checked. I haven't double checked it. It's whatever the bulletin says. Although now you get me all concerned and confused. Yeah. So I believe our class date is like, I think we're like the TR9 or WMW9 or something like that. So I forget exactly what it's called, but if you go and you look, whatever Monday, Wednesday at 9 o'clock, the classes that meet at those all have the same exam time. And so whatever time that is, I haven't checked to see if it's changed, but my bet is that it's probably still the same, but if I assume that, then it'll probably mean that I'll be wrong. So, all right, so today we're going to talk about the last sort of group of organic molecules we're going to discuss, and that's going to be polymers. And as we'll see, polymers, I think much in the sort of same spirit as a lot of the previous chapters, the sort of aim here, for me at least, is to sort of expose you guys to what polymers are, not necessarily turn you guys into polymer chemists, right? So I want you guys to be familiar with this class of molecules called polymers, sort of have a sense for how some of the different ones take place. And what we'll see is that really the polymerization, quote-unquote polymerization processes that we'll see are really just based upon a lot of chemistry that you guys have seen in the past. So when we're talking about polymers, really what we're referring to, right, are sort of macromolecules, and specifically macromolecules of repeating units. Okay, this can sometimes differentiate polymers from, say, for example, things that we might think of as like oligomers, right? So oligomers are also kind of repeating units, but generally compounds that we think of oligomers aren't necessarily defined. They can be repeating units, but sometimes they're not necessarily defined. So something like a protein or a sort of oligonucleotide sequence, right? Those are generally what we call as oligomers. But again, sometimes they're used interchangeably, so terminology isn't really that important. But specifically in polymers, what we're talking about is a series of repeat units. And they can really be classified into two sort of subsets of polymers. And so the first class is going to be step growth. Okay. Effectively, what these are going to be are molecules where generally you have, say, for example, right, some group where like you have two components, right, with two different functional groups, right, and if at the ends I have sort of functional groups labeled A and B, and for a system in which case A and B would react together, right? These are going to sort of form a bond, and what you'll be left with is right, this sort of series of sequences on and on and on. right? On and on and on. So basically from what you have is compounds which really have sort of symmetric compounds which have reactive groups, right? And it's sort of paired. So we'll get into some specific examples of these in a little bit. The other one is what we call sort of chain growth polymers. Okay, and so a chain growth polymerization process, we'll discuss some examples of this, but this isn't, it's not necessarily, I do a good job of board space there. But chain growth polymers are effectively, if you start with some type of a reactive group, right, you'll generally start with some type of a reactive compound, right, which oftentimes will have some component within it that will allow it to continue to react. So this is going to be a cartoon that's probably not very descriptive, but it's kind of like, you know, the same molecule will start building on itself. And again, you'll see there'll be differences within this, and when we see some examples, hopefully you'll understand what my sort of cartoon looks like here. But really, these are the two methods, at least in terms of subclasses, that we could think of. There's others, block polymers and so forth, but these are at least the two that the book discusses. And so these are the first that we'll discuss. Okay, and so for step growth polymers, bless you. Is that a sneeze or a hiccup? A hiccup sneeze? So under sort of step growth polymers, really a step growth polymer could really be anything that you could sort of imagine. If you can just think of two functional groups that could react together, you could start to imagine different polymers that are simply step growth polymerization processes. So I don't want to say it would necessarily be easy to be a polymer chemist, right? Because you'd probably have to find some utility to it, but I think that with just a little bit of creativity, and a knowledge of what's been out there in the past, you guys, even with the sort of skill set that you might have now, might start to be able to think of new ideas of polymers just based upon this principle of taking a few reactive groups and putting them together. So for example, you could imagine polymers where you have esters, where if, say for example, you have 1, 2, 3, 4. You have carboxylic acid like this, right? And you take that and you treat it with ethylene glycol. Right? And you begin to do some type of a, say, dehydration process, right? What's going to happen is you're going to make a whole bunch of esters along these molecules, right? So you'll begin to get molecules that looks something like right, and that's going to keep repeating, right? And so oftentimes what you'll end up seeing, right, is systems where you have something like this, and what you'll see often in the literature is that the way that you'll start thinking about these polymers is you'll take that repeating sequence, right, and you'll sort of bracket it. So as you're sort of looking at this molecule and you seek to find what the repeating units are in there, this oxygen, right, would be this oxygen here. So really what the repeating units are is from here over to here, right? So here's the component. Let me use color to maybe help see what's going on here. All right, so if we have, right, so there's this component here, you have the two methyls here, right? And then what's happening, right, is that this oxygen, right, you're making a bond here, right, between right? And then what's going to happen over here, right, is you're now going to start to have the other alcohol from the blue guy there, right? So the blue guy over here is going to continue, right? And that's going to end up being what would have otherwise been on that side. Well, this is from water, but if this sort of continued repeating, that oxygen would have been on that side. And so generally when you're looking at a polymer, what is something that's sort of important to be able to do is perhaps recognize the repeating unit. And then there's going to be sort of some number within this, right? And so these numbers will be fairly large, right? We're talking about hundreds, thousands, depending upon the polymer you would want. You can imagine that if you could sort of control the relative length of that polymer, maybe based on concentration and so forth, the relative size of that polymer is perhaps going to give it different properties, right? Because larger molecules are going to simply have different properties, right? We talked about things like, earlier, things like fats and so forth. And so molecules that might have 15 carbons might have different taste, for example. Well, I guess now we're getting to receptors and so forth. But certainly different physical properties as well. Something hexane, which has 6 carbons, is going to be a liquid, whereas something like ethane is going to be a gas, right, that only has the 2 carbons. And then meanwhile, larger, say, I don't know, the octane I think is still a liquid, but longer, a 20-carbon guy, now you're starting to get up to things that might have some solid components to them. And so the relative properties, right, of these polymers should obviously make sense that if you're sort of smaller, they're going to have different properties than larger, and so being able to control this is differently. But the other thing is that within polymers I think is worth mentioning is that you're never going to be able to, well, short of a controlled process, such as what we talked about in terms of peptide synthesis, these larger polymers, you're generally not going to have a single length, right? And so it's very difficult to sort of control if you're trying to make 1,000, right? You're never going to be able to be like, bam, there's 1,000. You might have an average length, right, of say 1,000 units, right? But what you'll end up getting in general, you get like a sort of a bell curve, right, of length versus percentage, right? And certainly a lot of chemists, what they really work to do is sort of keep that small, right? They try to have as uniform of a polymer as possible. And there's values that are associated with these that we're not going to go into. But certainly if you could have a narrower window so that they're all more uniform, that might have some benefits. But usually you're looking at the average, and the composite of that polymer is sort of what you're looking at. So you may have several different polymers. Maybe in this case, the best length is 1,000 units, but somewhere over here you've got 50 units, that there's maybe a couple, like maybe a 0.5% over here that's 50, maybe a 0.5% that's say 5,000, and then you get that sort of mixture in between. So you always get this sort of mixture of these polymers, and so in general, if you ever say, for example, order a polymer, we'll talk about polyethylene glycol later on, but sometimes you'll order PEG. Have you guys ever heard of polyethylene glycol? Have you guys ever had like cats that are, I don't know, to be gross in the morning, but like bowel issues? Like sometimes you'll put polyethylene glycol into their food, and you'll see it might be like PEG 50,000 or something like that. So what that is that's like the average. I'm thinking I might screw this up. I think it's the average mass. So like the average polymer mass is like 50,000 AMU. But that's just the average, right? There's going to be a variation from in between there. So it's important to recognize that polymers are dispersed among various different lengths. Okay? So this is a this would be a sort of a polyester, right? Because we're making ester bonds here. I think oftentimes, actually, in I think a lot of drug delivery, because esters aren't really that stable, they'll hydrolyze readily. So I think a few classes ago we talked about like delivery mechanisms. So sometimes they'll use esters because the esters will like slowly degrade the polymer, and then drugs will be released. Yeah. It does. That's the first step, right? Yeah, think about that. That's the first. The question was, why doesn't it react with the ester to form an acetal? And the first step in this mechanism, right, is to add in, generate that acetal, and then you're going to condense it into water. So, yeah. Okay. So this is an example of, this would be a polyester, right? Because there's a whole bunch of ester bonds there. As you would imagine, there's things like polyamides, right? So nylon, for example, is a polyamide. So if you take the one that's shown in your book. So instead of having alcohols as the reactive group, if instead you have, say, for example, how many carbons? 1, 2, 3, 4, 5, 6. Right, you can imagine if you mix these two together, instead of having esters, what you're now going to have is amides. Right, in this case, you're going to have a system like this, right, where you're going to have several groups of this. So this would be the repeating unit. Again, it would continue over here. You can see this is the nitrogen that would make up the amide on this side, so that would continue. This would be nylon. And again, this would be nylon 66. I don't know if nylon 66 might be, what's that? Sure, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Is that what it came from? Oh, I would have guessed that it would have been something different. But anyway, so fancy name. But anyway, so this is nylon 66, but I guess various versions of nylon might be different sort of derivatives of that. Maybe there's nylon 55, I don't know. But anyway, so the important point is here you have a system where there's amides, as you might imagine. It's simply based upon this. Now, an amide bond is certainly going to be more rigid, right, than an ester. So again, there may be different properties based upon having the amides being the linkers rather than the esters. Yes?
Yeah,
Thank you. Okay? All right. Okay, so that would be sort of polyamides. Okay, so there's, we could sort of go on and on and on here. But again, I sort of told you guys that I will try to get done a little bit early today. But this is, I guess the book does a lot of these. I'll show you one other. And again, you can look through a lot of these in your books, but it simply comes down to having one reactive group on one side and a different reactive group on the other. So another group that your book discusses is isocyanates. So we haven't really discussed isocyanates that much. So a group that has so this group here is an isocyanate. You can make them fairly readily through taking amines. So what you do is you take an amine and you treat it with phosgene, usually triphosgene. Phosgene is actually like a chemical warfare reagent. So you buy this, like there's a sort of a different form of this, more likely triphosgene. Basically breaks down to phosgene, but you take these guys and mix them together, and what happens is you get isocyanates. But isocyanates are fairly reactive. You have to actually, when you make them, you have to be sort of careful of like adventitious water and stuff, because the water will react with them fairly readily. See them a lot in biochemistry, not maybe biochemistry per se, but the thiocyanate is often used. Like you guys might start to see, and you guys go into biochemistry, fluorescein isothiocyanate, or which they call like FITC. Usually it's actually isothiocyanate, so it's fluorescein isothiocyanate. So instead of an oxygen, it would be a sulfur, and that's just a little bit more stable. But anyway, you can certainly take these molecules, and in the same way, you can imagine treating them for things like ethylene glycol, and again, now what you end up getting is compounds like right, and repeating unit in here. Actually, I'll take it out a little bit further. Right, so the repeating unit here would, I guess, be here, over there, right? All right, so this would sort of come from the isocyanate over on that side. So here's just another example. So again, I think this sort of step-through polymerization process, really all that it really requires is to identify a couple different groups. And so within sort of polymer field, you can imagine a lot of polymers that have developed. People would sort of look at two different reactive groups. They might mix them together at various concentrations, see what type of polymeric mixture would come out. And then if they got lucky, maybe that polymer would have some properties that they might find sort of useful. Right? I think the story of silly putty. Right? You guys heard of silly putty? I forget. It was like I forget what the polymer was that they were trying to make, but they were doing this kind of stuff, right? It was like, let's make a polymer, let's see if it has properties that are useful, and they were trying to generate a specific type of polymer. I don't remember what, but they had their eyes set on this certain thing. They generated this polymer that was sort of silly putty, right? It was that sort of feel to it, and I guess one of the scientists that was there, I guess, said to the people that sort of owned it, or, you know, this is kind of neat. Are you guys going to do anything with it? And they're like, no. So they didn't bother patenting it. So the guy was like, well, I'm going to go ahead and I'm going to patent it, and I'm just going to, you know, advertise the crap out of it. And so he took it, made it pink or blue or whatever colors, and it became this huge kid toy, right, that people use a lot. And so again, that's a lot of what I think polymer chemistry is. It's sort of like develop the polymer, see what the texture is to it. And again, this stuff is used in a lot of different things. I remember when I was an undergrad, we were talking about the strength of, I remember this because it was just kind of funny how, I don't know, I don't want to say naive or whatever, because I think this isn't necessarily naivete, but I didn't really know about polymers that much. But what I knew, I think it was an undergrad, and I knew that organic molecules, like the strongest interaction was like a bond. And I don't remember what was happening, but I was like, wouldn't it be awesome if you could just make one huge molecule just full of tons and tons of bonds? And somebody's like, dude, that's what polymers are, right? So it's like, oh. So finally I had thought of that 80 years previously, maybe I could have been a wealthy individual. But certainly you see this stuff in like Kevlar, right? So like bulletproof vests, because that's what I was thinking. I was like, you could have something to stop bullets. And it's like, yeah, people have done that, right? So you have polymers that have properties that are, you know, flexible, right? This is a polymer here, right? Any plastic bags or things like you have, that's going to be polymer. And it goes everywhere from there to things like silly putty, to things like Kevlar or bulletproof jackets and things like that, things that are meant to withstand, or, you know, the linings of airplanes, right? Well, actually, those are probably steel, but there's probably components within them like polymers as well, and I'm sure that there's polymers within aviation vehicles as well, and things that are necessary to withstand things like high temperature changes and so forth. So again, this is sort of, you could imagine how, with the sort of just the knowledge base of this, you could begin to start a company, right, based upon polymers and stuff like that. So, all right. All right, so this is the one type, step-through polymerization, that you'll see from time to time. The other one that we'll sort of see is chain growth polymerization. Okay, and in general, what a chain growth polymerization process is it's a system where an initial reaction takes place, and that's going to set off a series of further reactive properties. So I thought I would start with the kind of fun one that the book discusses, which is superglue. Okay, so superglue So when you get superglue, right, what you actually have is a molecule. Draw it right. Not quite sure what R is. You have a molecule like this, right, and it's kept dry. It's kept it within a the container, absent from any water or anything like that. And what happens is you have this, and maybe it's in the suspension of some inorganic solvent. I'm not really sure how it's comprised. I just want to tell you a little bit about the chemistry. But what happens in superglue, right, is that you sort of put it onto whatever you want to glue together, and there's always going to be some adventitious water, right, that's in the air. And so one of the most common misconceptions about superglue, right, is that you're sort of waiting for the glue to dry, when in fact it's kind of the opposite. It's sort of like you're waiting for water to actually initiate a process that's going to take this single molecule and turn it into a polymer. And so what happens in superglue is that you get an initiation process where you have a really good electrophile right there, right? And what's going to happen is the water is actually going to add in. Okay, and again, you're going to have, we can push it onto either side of this, right? And I'll just sort of show the anion on the central carbon. And this is the sort of key point, I think, of, and then we'll just sort of minus equivalent of water. But what's going to happen here is at this point, right, you're going to have this molecule, which is now a nucleophile, right, which can now react with an electrophile. So let's see what happens when it does that. Right, if we take these lone pairs, now this could react through a Michael reaction. Right? Now what's going to happen is right, you're going to generate now you've gone from a monomeric unit with a nucleophile to a dimolecular unit, or what, I don't want to say dimolecular, but you've basically added in, generating a new nucleophile that's now got two of those units in it. And then you're just going to keep doing this over and over and over again, right, until you get to that sort of polymeric structure. So you'll end up getting something like right, on and on, and then probably then you'll sort of quench it. But again, you're going to have a series of these repeating units. Again, it's kind of easy to identify the repeating units in this scenario, right, because the repeating unit is literally the compound that was sort of the initiator. So as long as you can sort of identify the substructure in here, you can sort of identify that. Okay. I'll show you guys a few more. But while I'm thinking about it, does anybody know, I guess there's a few, anybody know like one of the very first polymers? What's that? Well, polystyrene's been around for a while, but even before them, like not, what's that? Bakelite. Bakelite? don't know what's Bakelite. I don't know. Oh, no, I'm not talking about synthetic. This predates even that. Yeah, like rubber, right? Like rubber is probably, that's what I was trying to think of, is probably one of the very early, polymers. And if you actually look at the structure of rubber, what you'll see is that rubber is actually a terpene, a polyterpene compound. So if you ever look at the structure of rubber, it's slightly different. They do there's usually like a few isoprenyl units in one direction, and then it flips over to the other direction. It just makes like a huge polymer in the other direction. But you'll see like polymeric systems and within like rubber as well. So, all right. All right, I'll show a few more chain growth polymerization processes. So again, the way that this works, right, is that you have to initiate it, and the way that superglue works, right, is that you have this sort of water as the initiator, it adds in, and then eventually it sets off this process. And so now you can imagine, right, if you leave the cap off of your superglue, right, what's going to happen, right, is that water will get in there, and will set off a process, and then your entire glue will be ruined because it will all become hardened into this polymer, right? So. All right. Now you guys were talking about polystyrene, yes? What do you think? Yeah, you would probably need a spray bottle, right? And maybe the mechanics of the spray bottle won't work because you're subsequently in a vacuum. So, yeah, I don't know how you would use super glue in space, but I'm sure that people could figure out how. Yeah. Okay. So polystyrene was just brought up. So polystyrene is another one that you guys have probably heard of. And so what is styrene? Some of you guys might know this, others may not know. Now you all know this is styrene, right? So it's basically benzene with an alkene group off of it, right? And so what happens, and there's a few different ways that you can sort of initiate polystyrene polymerization processes. And perhaps one of the more common ways to do it is to initiate it with, say, for example, an acid. So if you want to do a polymerization process with polystyrene, what you would do is you would take the molecule, you would treat it to acid, right? And we've seen this chemistry in the presence of water, right? You would add water across that double bond, but if we're under dry conditions or if we have a concentration, high concentration of styrene, what's going to happen is the very first thing that's going to happen, right, and you guys should be familiar with this, is protonate. Again, that's organic chemistry 1 scenario. Now what you have, right, is a electrophile, right, a second equivalent of this can come in, right, and react. I'll start abbreviating this as phenyl. No, I won't. Okay. Right, and so then what's going to happen is another equivalent's going to come in, right? And so over time, what you're going to get is a sort of a series of these styrenyl units, right? So you've got the styrene here, you get the styrene here, right? And that's going to keep growing out. And again, depending upon, probably at the end, you're not going to hang around as a cation. Probably what will happen at the very end is you'll maybe quench it with water or something like that. So a lot of times, that's one of the ways, one of the things that you can do with, say, for example, chain growth polymerization processes is you let it go under certain conditions, and for example, depending on how long you let the process go, right, the chain might grow longer or shorter. So you can actually, one of the advantages to chain growth polymerization processes is something like time can be used, right? So yeah, if you don't use up all of this, if you end up using up all of this, then all bets are off. But if you have a certain amount of this, or say, for example, a certain amount of styrene or a certain amount of this acrylate in your solution, and you have it in large enough excess, then at certain time points you might be able to sort of quench that process, right? So in a situation like this, maybe it might be challenging, but what you can imagine doing is adding, for example, an acid or some type of other electrophile in there that would get trapped by this, right? So if you, say, for example, quenched it with, I don't know, trifluoroacetic acid or something, you're going to quench that, and then you'll have, say, 30 units rather than 100 units, or 100 units rather than 1,000 units, or 1,000 units rather than 10,000 units. But if you let it go longer, then you can start to get the longer ones. And the same thing like here, right? You might quench this, you have this cation, well, what are some of the things that could quench that cation? Well, some type of a nucleophile, maybe water. Whereas water initiates this one, maybe water would trap this one out, or something like that. Yeah, Mark?
So what does it say that you have more than one molecule without all initiating the reaction? Then someone can end up with a longer, bigger molecule, others end up with a smaller molecule.
Yeah, so what you're talking about is mixed polymers. So even like with polystyrene, so a good example of that would be one of the things. So we were talking the other day about beads in terms of doing amino acids on beads, and the sort of classic resin, if you will, where people did peptide chemistry on is Merrifield resin, okay, which you guys may have heard of. And what Merrifield resin is it's effectively a polystyrene bead, right? So it's a polymeric polystyrene. But what they have in there is a percentage of, they have the styrene, but they also have in there some of this chloride, right? So maybe this kind of helps answer your question. So you get a mixture, right? It's some random assortment of that, but there's going to be some percentage of these side chains will have a chloride hanging off of them and others won't. But you'll get a bead, some of it will have this, some of it won't. And then in the Merrifield resin standpoint, they basically use that chloride as an attachment point to put their peptide so that they can grow off of the peptide. And so you can certainly do mixed polymers as well. Right? Now, one of the things about polymerizations, especially in situations like this, is that oftentimes, it's not time for a Ryan story, Professor Morelli's story of his research experience. Sometimes polymerization can actually not be something that you want. And when I was a graduate student, actually when I was a postdoc, I was making this compound that looked something like, it was like phosphate, something like, I don't know if I'm going to get this right or not, but it's something like this. We were trying to make, I probably screwed it up in some way, but it was something like that looked like this, and we were interested in putting a group over here. We were interested in putting an alkyne over there, I think. We were doing this appendage. And the way that we made this, if I remember right, there was a lithium aluminum hydride reduction at one point, and I forget, maybe it wasn't even this, maybe it was the free alcohol. But you'll see in here you have this sort of styrene. And I forget exactly the chemistry that we were doing. But I had done this chemistry, and a graduate student, he was a first-year graduate student, I was sort of first-year postdoc, and we started working on this a little bit together, and he was doing this reaction as well. I was sort of showing him how to do it, and at this one step, I didn't really have any issues with it, and he continued to have issues with it. And what would happen was it would just crap out on him. So it would just get really, really crappy. And he would go down and take an NMR, and all the peaks would just look like crap. And meanwhile, I would run it, and I would get this beautiful NMR, and everything was defined in there, and things looked great. And for a while, it was kind of confusing, because it was like, why is it not working for you, and why is it working for me? And at a certain point, what we realized, or what I sort of realized, was that this molecule had this styrenyl group in it. And he was just starting off as a graduate student. The things that he was doing were taking him a little bit longer. So when I was doing it, I would make this compound, I would immediately take it up in chloroform to take it on to go down and take an NMR. And so I was never letting it sit dry. Like I would make it, and I would have still some little bit of solvent in there just because I was trying to move on. And he was trying to be very meticulous, and so he was pumping it down on the vacuum, making sure there was no solvent in there and everything else. And what was happening was, as it was sitting on that pump completely dry, this was polymerizing on him. So what was happening was this sort of internal group here was just, again, that's what was happening, was it was polymerizing. And so at the moment that we realized that, I said, okay, don't take it, don't let it fully dry, don't leave it on the pump for 5 to 10 minutes like he was doing. And once he started doing that, everything was fine. This project, we went in a completely different direction, so it's kind of irrelevant, but it was kind of interesting sort of story where you sort of see that. Now, what's interesting about this molecule that was giving us issues is a fairly common one, and what would that be? What's the mechanism over here? What's the sort of initiation step of this polymerization? Protonation, right? That's going to make it much easier to protonate, right? Because now you can resonate down. And so now you're able to protonate much, much more readily. So it's very difficult sometimes to make organic molecules that have styrenyl units in them as well as things like ethers in them as well. These will just sort of take off through polymerization process again because you have that sort of resonance donation. So electronically rich styrenes are very, very difficult to sort of make and work with, again, because they'll polymerize readily. So that's sort of worth mentioning. All right, so what are some other polymerization processes? So this would be a sort of an acid followed by a series of nucleophilic additions. Another one that's fairly common is radical growth polymerization. So if you can sort of initiate a molecule based upon a radical, obviously that radical could perhaps add across a variety of different components. And so sometimes you'll see actually polystyrene driven by radical processes. Does the book have a specific version of this? Yeah, so the book discusses like polyethylene, right? So if you have sort of just ethylene, right, you make huge polymeric chains, and so ethylene in itself might not necessarily do anything, but in the presence of a radical catalyst, you can begin to get to polymers where your sort of repeating unit is this sort of ethylene unit. And so sort of the ability to initiate a radical is often important in this standpoint. A fairly common one that you guys have probably seen in the past is dibenzyl peroxide. Right, some ways that you can get access to these radicals, right? So in this case, what happens is you have this component which can actually undergo homolytic bond cleavage, right, generate a radical, right? And then once you have that radical and you've got a whole bunch of, say, an alkene around, right, that radical can now begin to add across the alkene. Right, and now you still have that radical, and it's just going to add it across another. Right, and you're going to keep going and going and going. And on and on and on. Right, so you'll just get this sort of overall process here. Again, a situation like this, you could imagine quenching with some type of radical scavenger. So, you know, maybe even something, these might be able to terminate on their own based upon elimination chemistry or stuff like that. But oftentimes things like a common radical quencher is like tributyltin hydride is fairly commonly used. There's a bunch of them, but there's things that will just sort of trap that radical for you. Okay. Oh, sorry, in this case it actually breaks down even further. So this wouldn't be what you had, sorry, that was my bad. So this, wow, I just botched that completely. So this breaks down to lose CO2. I just skipped over that accent. Sorry, and this is important. That's a semi-important point, right? So the idea here is that the sort of formation of the radical, the sort of stabilized radical, might not be reactive enough to add across the alkene, right? But the important point here is that you generate a radical. I think that's the take-home point that I want to make, is that regardless of whether you do it with that or with this one, the point is that you generate that radical, and then once you have some type of a radical species, you can sort of get this systematic addition across these bonds. Okay, so that's radical. I'll show you, I think, two more. I'll show you two more, and then we can actually maybe get out a little early. Talk a little bit about polyethylene glycol. So we've seen now, just trying to show you a few mechanistically different ones. So we saw acid, we saw sort of acid-initiated chain growth polymerization. We've seen radical-initiated. There can also be nucleophilic-initiated. Polyethylene glycol is a good example of this. Actually, the superglue is also an example of this. But here's another nucleophilic example of polyethylene glycol. So if you have ethylene oxide, so this is ethylene oxide, just the sort of standard epoxide, the most simple epoxide that you can have, and you treat it with a nucleophile, such as hydroxide, what's going to happen is you're going to open up that ring. And we've seen this previously, right, in probably last semester, or last time we took organic. When we took organic 1, we saw this, right? And what's going to happen then is you're going to now have a new alkoxide, right? And if your concentration of this is high enough, right, what's then going to happen is it's going to add to another one. Right, to generate a new alkoxide, and then that's going to add into another one, and on and on and on. Right, and so what's going to happen is at the end of the day, you're going to have a sort of set of repeating units in there that are called sort of oxyethylene units. And so, so again, sort of polyethylene glycol is so ethylene glycol, right, is this compound. Polyethylene glycol is just a series of that sort of repeating unit throughout that system. So this is PEG, if you ever hear of PEG polymer. And again, many of you that are sort of perhaps interested in even research within, say, biochemistry and stuff like that, you'll sometimes see polyethylene glycol are really useful side chains. They have all of these oxygens in them, and that actually makes them fairly water soluble. So polyethylene glycol actually is fairly water soluble because of this, because of the network that you can have of these. And so a lot of times people will, if they want to, say, for example, make probes where one thing might bind to something and another part might bind to something else in a sort of an aqueous environment, they'll make the linker sort of polyethylene glycol. So very, very commonly used nucleophile, or sorry, polymer. All right. And the last one that I figured I would talk about is metathesis, ring opening metathesis polymerization. So this sort of gets back to so, I don't know if I mentioned this when we were talking about metathesis, but a lot of the really early work on metathesis was, well, actually a lot of the earliest work was completely serendipitous. They were trying to do something else and noticed this these new polymers, but it was within polymer chemistry. They were trying to make a specific type of polymer, and what they were finding was a different polymer that they couldn't make sense of based upon the chemistry that they were doing, and so it then led to their discovery of a new catalytic method that is metathesis. And so a lot of these sort of initial work on metathesis reaction, even though now it's become very controlled and sort of small molecule organic synthetic chemists use metathesis a lot. The sort of earliest work in metathesis was, in fact, polymers. And if you ever see a Bob Grubbs talk on metathesis, generally what he'll have is this. It's kind of neat. I don't know if he still does it, but when I saw him talk about 10, 12 years ago, he brought this block polymer that had a bullet just lodged in it. And he handed it around. So everybody was handing around this polymer with just a bullet just stuck right inside of it. And so they had clearly taken this thing and shot a bullet into it, and it stayed intact, even though it absorbed the bullet. And so a lot of times this sort of strength of the polymers that you generate are based upon the bonds you have within there, and so something like an amide bond or an ester bond, again, might not be as strong as, say, for example, an all-carbon side chain, which might not degrade as readily, right, because it's harder to break carbon-carbon bonds. A lot of the sort of work in terms of initiating these radical polymerization processes within metathesis are based upon highly strained alkenes, such as the one that I've shown you here. And again, this is sort of from early on when the metathesis catalysts actually weren't all that active. They're certainly much more active now, so they can make other catalysts, but a lot of the early work effectively required them to gain entry to be able to have something that would react with their metal alkylidine. So we were talking about the ruthenium carbon double bond, and so in order for that to react with an alkene, they wanted a highly reactive alkene. And so this is a very highly strained alkene, so it will react. It's also everything else is pulled back, so it's perhaps a little bit more exposed. What happens is when you take this and you treat it with, say, for example, that metal carbene, and again, for the final, you're going to want to know this mechanism, right, of metathesis catalyst, right? So this is you can pretty much expect to get either a mechanism question based upon metathesis or a mechanism based upon cross-coupling, right? So we haven't been tested on those, so you can expect a mechanism question based upon this or cross-coupling. Okay, and once you get to this step, then what happens, right? So it does the 2 plus 2, and then it does another 2 plus 2. Right, so now it pops open, and you have a new alkylidine, right? And now this new alkylidine can now react with a second equivalent. Right? This is going to open up. Now I have two of these together. And you can all see where this is going, right? Now we're starting to, we've got now two compounds that are like this. Right? And then you can keep going on and on and on and on. So you basically generate this polyene structure of a sort of a polymer that is connected all through sort of these sort of carbon bonds. Okay. Viscosity Lernata. Yeah, so that's basically it. Again, your book is going to discuss certain other aspects, but again, you can begin to see a lot of these structures sort of are initiated by various things and then set off different sort of processes. So again, if you have a sort of a solution of styrene, what you'll find is over time the styrene might start generating solid at the bottom. And again, it's because it's starting to crash out on you as a polymer. Acrylates will often polymerize fairly readily. They'll often need to be stabilizing in there because the moment that you generate a radical, right, it'll set off a sort of a range of polymerization processes. So, so this is polymer chemistry. This really wasn't too much of a chapter, and you've seen that I think a lot of the chemistry is just based upon what you've seen previously. So amide bond couplings, as you can imagine, would be used to make some of those previous ones. Certainly metathesis is based upon the reaction you've seen previously in that respect, ethylene oxide, and some of these others and so forth. So, all right, so with that, I guess I'll sort of end class now, and I'll be up in my office, in probably 5 to 10 minutes. If you guys want to start, those of you that might want to come to office hours. So, and again, email me if you want me to focus on anything in particular for sort of next class. So, okay.